Hey everyone! So in this video, we're going to introduce ourselves to a little vector algebra. So one way that we referred to vectors in the last video, in the last couple, was by the starting point and the ending point, the initial point and the terminal point. And if we want to find vector AB, but they're giving us the initial point and terminal point, what we can do is we can graph them. That's one way of doing this. So if I graph this and graph A at 2 comma 1 and graph B at negative 4 comma 0, I want to ask myself, this should have this guy over the top, but my computer doesn't have that symbol for some reason. So we want to find what vector AB is. Vector AB is essentially, how do I get from A to B? Well, I would need to go left, 1, 2, 3, 4, 5, 6, so negative 6i, and then down 1, so negative 1j. When there's just a 1, we typically don't put the 1 there. Although, if I am writing it in the vertical matrix form, then I would write negative 6, negative 1. Those two forms are the forms that are used most often for IB. Another way to do this without using a diagram is just to subtract vector B's point from vector A's point from vector B. So negative 4 minus 2 gets you negative 6. 0 minus 1 gets you negative 1. So that's a way to do that without having to draw a diagram on a coordinate plane. One more thing to talk about before we move on, and that is what we call a position vector. Sometimes they'll call it a vector in standard position. Sometimes they'll use that phrase as well. So if they use the term position vector or a vector in standard position, what they mean is that they want you to put that vector at the origin. So let's say I had a vector 4i plus 3j, and they wanted me to put that in as a position vector. So I would start at 0, 0, go over 4 and up 3. I'll just guesstimate what that would be here. So this would be a vector in standard position. We typically use O as the origin, and let's just come up with some other point for this guy. So let's call it OR. So vector OR would be 4i plus 3j. Okay, next up, what if you are given some of the points of a parallelogram and you are supposed to come up with the fourth point of the parallelogram? So you might as well just start with what you've got, I suppose. So put the 3 points you do have on a coordinate plane. So I've got negative 2, negative 1. That's point A. 3 comma 0 is point B. And 0 comma 2 is point C. Oh, point D. When you say the name of a parallelogram or any polygon, those letters are connected in that order. So A gets connected with B, B will then get connected with C, and then C will get connected with D, and then D back to A. So it does have to go in order. So we're missing point C, which would need to be somewhere in this area. How do I know exactly where? Well, use what you know about parallelograms to your advantage. I know that the opposite sides are parallel, so whatever AD is doing, BC has to do the same thing. So AD is up 3 over 2, so BC has to also be up 3 over 2. So that's how you can find the position of that point on the graph. You can just use logic and common sense from what you remember from geometry. So we know that the answer is 5 comma 3. But what if you had numbers that were too large to do that? Or soon we're going to start working in 3 dimensions. What if you had 3 dimensions and you had to figure out the fourth point? Let's figure out how to do this algebraically instead. Well, one thing we know is that AD is right 2 up 3. And let's just do it from here. Right 2 up 3. It's going to the right 2 and up 3. Right 2 and up 3. And we also know that whatever is happening with AD, BC has to be the same thing. So BC also has to be to the right 2 and up 3. That's just following the properties of parallelograms. So if I started at B, which is at 3 comma 0, and I went to the right 2, I would now be at 5. If I started at B and the y value is 0, and then I went up 3, I'd now be at 3. So you can use the vector that's opposite from it to figure out what the missing point will be. So that is how you can work that up. So let's try that now with 3 dimensions. This is not really something we can draw really in 3-dimensional space, but we can at least draw ourselves a little diagram to give ourselves some perspective. So I have A, B, and C. So I'm just going to draw myself a generic looking parallelogram. And my task is to find out point D. So A is 1 comma 2 comma 1. B is 3 comma 4 comma negative 2. And C is 2, 7, negative 4. So I want to find the coordinates of D. So here's what I'm thinking. I'm thinking that I know I could figure out what BC is. So BC is the vector where I just do C minus B. So I do 2 minus 3 and get negative 1i. I can do C minus B, so I'm doing 7 minus 4 plus 3j. And now the third dimension. So I is 1 unit in the x direction, j is 1 unit in the y direction, k is 1 unit in the z direction. So I'm going to do C minus B here, so negative 4 minus negative 2. So negative 4 plus 2. So minus 2k. So that is my vector BC. But that's also going to have to be the same thing as vector AD, because they're on opposite sides of our parallelogram. So I can use that now to figure out where point D is. D is simply going to be starting at point A and then moving along vector AD. So I'm starting at A, I'm moving along this vector, and I'm ending at D. So let's see what we've got. We've got 1 comma 2 comma 1. And then I'm going to subtract 1, so I'll get 0. I'm going to add 3, so I'll get 5. And I'm going to subtract 2, so I'll get negative 1. So that means that D is at 0, comma 5, comma negative 1. So even when you don't have a physical graph, you can still draw yourself a diagram that will be helpful, and then use the properties of vectors to figure out what's missing. Next up, magnitude of a vector. Magnitude is just a fancy word for the length. Sometimes they'll also say something like distance. They'll be like the distance from the initial point to the terminal point. So magnitude, length, distance are all synonyms here. So the formula in your booklet is given with vector v. So that's what we're going to do. So in 2 dimensions, it would be, we have some vector v. So this is vector v here. Notice that vector v will form a right triangle if you drop down to the axis. So if we think about the components of vector v, the x component, let's just call it v1. The y component, let's call it v2. By simply using the Pythagorean theorem here, we can substitute those in. And the way that we typically will write this when we square root both sides here is we write the magnitude of vector v is equivalent to the square root of v1 squared plus v2 squared. So I'm simply square rooting both sides here, which will isolate vector v. But to show that we're finding the magnitude of vector v, we'll put these little absolute value bars. Absolute value bars are magnitude bars. Because think about what's the absolute value of negative 5? 5. It's the magnitude from 0 to that number. So it's absolute value bars, but that's like the same thing. So that's what you put to show magnitude. Now, what about 3 dimensions? 3 dimensions are just an extension of the 2 dimensions. So instead of doing v1 squared plus v2 squared, you do that, but then you also add v3 squared, which would be the k, or vertical component. So let's practice that a bit. We're going to find the magnitude of vector A. Remember, there are 2 ways to write the names of vectors when they're just written as single letters. When they're written with 2 letters, we don't need to worry about bolding them. We always just do the arrow over the top. When you're writing the vector name as 1 lowercase letter, you can either make it bold or put the arrow. Okay, so I'm going to do v1 is 3, v2 is 5, and v3 is 2, negative 2. The negative will just cancel anyway, so I sometimes don't even write the negative part. And then I square them and add them all up. So square root of 9, the square root of 3 is 9, the square root of 5 is 25, and then 4. So I end up with the square root of 38. And that's typically how we'll leave that. If it does simplify, then yeah, they expect that you will. So like if it was rad 8, you should write that as 2 rad 2. And typically we do leave them as radicals because we usually want the exact value rather than something that's been rounded. Next thing, find a unit vector. Whenever you just see something like unit circle, unit vector, it's a vector of length 1. It's got a length of 1 unit. So they want it to have a length of 1, or we should say magnitude, right? So here's what we do. We take this vector A. Now we know that vector A, let's just say it goes off in this direction. Vector A has a magnitude that's radical 38. That's how long vector A is. That's longer than 1, right? It's about 6.1 probably. We want to shrink that down so that it doesn't go as far. How far do we want it to go? 1 unit. So we want the vector that's going the same direction as A, but only 1 unit long. The symbol that we use for a unit vector in a certain direction is with this little hat on top. It's like a little caret sort of thing. So this is the symbol for unit vector. So it's the same vector we started with, but we've shrunk the vector down so it has a length of 1. How do we do that? Well, all we do actually is take our component form and we divide each component by the magnitude of A. So 3i over rad 38, 5j over rad 38, minus 2k over rad 38. And we do not typically rationalize these. You can leave it just like it is here. So vector A has a magnitude of rad 38. Unit vector A has a magnitude of 1. If we plugged these components into the magnitude formula, it would work out to be a 1. If you don't believe me, check it. Okay, we have 2 more problems to finish up with here. Now, we want to still use vector A, but we want it to have a magnitude of 6. Well, we can change the magnitude of the vector we have to anything we want. What we do is we first scale it down so it has a magnitude of 1. That's this. So what would I have to times this by so that it will have a magnitude of 6? Yeah, 6. So 6 times unit vector A. I'll just times each of these components by 6. So I'm just timesing, I don't know why I wrote that twice. I'm just timesing each of these by 6. So I get 18i over rad 38 plus 30j over rad 38 minus 12k over rad 38. Okay, one final problem. This time they give us 2 vectors, negative 7, 6, and k, 2k. And we are supposed to find the values of k so that the magnitude of c is twice the magnitude of d. Well, we really just fill the numbers in the formula here and then solve it. So the magnitude of c is going to be the square of negative 7 plus the square of 6. The magnitude of d, notice I'm just carrying the 2 down here, will be k squared plus 2k squared. So let's see, over here on the left, I'm going to get 49 and 36. So 59, 69, 79, 85, 85. So I get rad 85. Over here, I'm going to get 5k squared because I've got k squared plus 4k squared. So now my goal is really just to get k alone. So one of the things I could do, I suppose, is square both sides. So that way I get 85 equals 4 times 5k squared. Don't forget to square the 2 if you're squaring both sides. And then I could divide both sides by 20, because that's what 4 times 5 is. So 85 divided by 20, those are both divisible by 5, so I'm going to get 17 over 4 is k squared, and then I will square root. So I'll end up with the square root of 17 over 2, but remember, we've got to do plus and minus on that, because both of those values would make that statement true. Notice they implied that in the question. Find the values of k. Okay, so that's a little bit of an introduction to vector algebra, and we'll pick up from there in the next video.